All right, so we are going to start the second part of our chapter 4 lecture. Remember in the last lecture we talked about the Boolean expression, right? And we also have shown that how to convert between truth table and the circuit and also the expression. So we'll also talk about more today. So the first one that I have here is from digital circuit to truth table. Okay. Now before I start here, let me remind you one thing. That in digital circuit, for every digital circuit, you can, of course, draw a circuit. You can also represent the circuit by a truth table. You can also represent the circuit by an expression, which is the Boolean expression, right? So that means that every Boolean expression also has a circuit and also has a truth table. So all this means that if you are given a digital circuit, you should be able to find the truth table and the digital circuit. If you are given a circuit, then you should be able to draw the truth table and also the Boolean expression, write the Boolean expression. And if you are given the Boolean expression, you should be able to find the digital circuit and also the truth table. So that means that digital circuit, Boolean expression, and truth table, all these three different things are equivalent to each other. Okay? So if you are given one of these three, you should be able to find the other two. Okay? So which is quite different than electric circuit, because in the electric circuit we don't have any expression that can represent the circuit, right? We also don't have even truth table. Okay, now, so here we are trying how to convert the digital circuit to truth table. That means that if you are given a circuit, how can you find the truth table? Now, before I look at this circuit as an example, let's look at the circuit carefully. How many variables we have here? 3 variables. So from there, we already know that in our truth table, we'll have 3 columns for the input, right? A, B, and C. Now, so we already have drawn A, B, and C. Just recall the last, remember the last class we talked about how to write this combination, right? One of the easiest combination is we can try to write the binary numbers, right? So the first number we wrote here is what? 0, binary 0, 1, 2, all the way to binary 7, right? And how do I know that I have 8 combination? I just have to do 2 to the power number of input, right? So I have 3 inputs here, so it's 2 to the power 3, which is 8. So that means I have to write Boolean binary 0 to binary 7, right? Which are the 8 numbers. So if I have 4 inputs, then I should have 2 to the power 4, which means 16 combination of input, which means I'll be writing binary 0 to binary 15. Now, so I already know the A, B, and C column, which are pretty given, like all the time is same. The only thing that I have to find here from the circuit will be the column X, which is the output column. Basically, every circuit, you actually have to find the column X. So in pause, when you'll be answering the question like this one, all you have to enter is just the column X, because that is the only column which makes the difference. All right, so let's see how we can find the truth table from this expression. So let's look at the very first row here. In my first row, I have 0, 0, 0, right, for A, B, and C. So what I'm going to do is I'll plug 0, 0, 0 in my circuit. So the first gate here at the left side, this is an OR gate, right? So the OR gate gives you what? 0 for the input 0, 0. And the second gate is also OR gate. So my C is 0, and the line here coming from the other OR gate is also 0. So the 0, 0 again gives you another 0 at the final outcome, right? So that's how I know that what will be my column X for the combination 0, 0, and 0. For the row 2, now I have 1 for C and 0 for A and B. I did pretty much the same thing. So I plugged 0, 0 here, and for the OR gate I got a 0. But for the second OR gate, I have 1 here for C, right? And then 0 is coming from the other OR gate, which will give you a 1, because the OR gate gives you 1 if you have 1 in any of the output or both of the output, right? So the final outcome is 1. So that's how I actually plug 1 at the column X for this row 2, right? In the same manner, I can pretty much I can pretty much fill all the rows based on every single combination of the inputs, right? So again, as I said, once you're given a circuit, you can definitely find the truth table from here, right? So I just randomly selected some rows. So you can always find different rows, right? So I just selected row number 7 just to show you another example. But you have to fill all of the rows. I just selected something randomly. So in the row 7 I have what? A is 1, B is 1, C is 0, right? Once I plug that, again as you can see, for 1 1 in the first OR gate I get 1. In the second OR gate I have 1 here, I have 0 from C, and that will give you a 1 again, right? So the output is 1. So you can fill pretty much the whole column, right? So for all combinations. So now I know that from any digital circuit, we should be able to find a truth table, right? Any question? It's actually very simple. All you have to do is for every row, you have to do just one calculation based on the circuit you are given, right? So this will cover your next quiz, which is chapter 4, quiz number 6. Let's try something else. Again, as we said before, that all these three, logic, the Boolean expression, sometimes we call it logic expression, digital circuit and truth table are equivalent to each other, right? So we are trying all sort of conversions between all these three items. Now let's try to write an expression from the Boolean circuit, from the digital circuit. So that means if you are given a circuit, how can I write an expression from the circuit? Okay. Now again, don't forget that for every gate we have an expression, right? We can write an expression for every gate. So let's look at here what I have. So I have 3 inputs A, B, and C. At the very left side I have an OR gate, and I have 2 inputs for the OR gate, right? Which is A and B, A and B, right? Now what is the OR operation? How do you represent OR operation in the Boolean expression? Plus, right? Remember the plus is the OR operation, right? So that means this OR gate will produce the expression like this, right? A plus B. And the other input I have is C. Now for the next gate, that is also an OR gate, which will produce A plus B plus C, right? So basically my output column, meaning the output for this expression is A plus B plus C. So in pause, whenever you will be answering this question, you can either write A plus B plus C, or you can write X equals to A plus B plus C. It doesn't matter, okay? X always stands for the output in this class. So we just, sometimes write X, or even if you don't write X for the output in such expressions, this will still work. Okay? Let's try another circuit. This is a little bit bigger than before, okay? And we also have different variants of gates here. So instead of only having like OR gate in the last example. Now, again, we most of the time start from the gate where we can get the expression right away. So for an example here, if you look at the gate, the AND gate, right, here, so you have direct input to this gate, so which is C and D. So again, let's recall, what is the AND operation in Boolean expression? It's a multiplication, right? C times D, right, which means C dot D, and then we do not write the dots, just like the traditional algebra. So instead of writing C dot D, we can just write CD, right, which stands for C dot D, so Boolean multiplication. So let's look at the next AND gate here. This is also an AND gate, so we have one input coming from here, which is CD. Another input is B, right? So again, if you do an AND, it will be B times CD, right? So there is actually no ordering, so you don't have to write BCD. If somebody writes CDB, or if somebody writes CBD, all of these are correct, okay? But just for the sake of pause, we try to write in alphabetic order, but it doesn't have to be in alphabetic order, okay? So in the other AND gate, we have another input combination A and B here, which will produce AB, right? It's just like any AND gate. Then the final gate at the very right side is an OR gate. And again, the OR operation means what? Plus, right? So one input is BCD and the other input is AB, right? So it will just add both expression, right? AB plus BCD. That's how, given any digital circuit, you should be able to find a logic expression, which is also called Boolean expression. Okay? So this is very interesting in the digital circuit. So no matter how big is circuit, you should be able to always represent the circuit using a simple expression. Okay? And at some point you'll feel like if you're given the expression, you should be able to draw the circuit as well. That's pretty much the same thing, equivalent to each other. Any question? This will cover actually 3 different quizzes. The reason we have 3 quizzes here, because as you have realized that we have different capacity of, I'm saying different size of circuits. Some of the circuits are a little bit bigger, right? So we want to, try different kind of circuit. And the bigger circuit will be, the expression will be more longer, right? So we want to check with multiple different types. So that's why we have 3 quizzes for this part. Now, again, all the Boolean digital circuit runs on logic, right? We already have some idea about the logic, because all the gates that you have seen, like inverter, basic gates like inverter, OR gate, AND gate, and other gates like NAND gate, NOR gate, exclusive OR, exclusive NOR, all these gates runs on some logic, right? Because every gate has a logic, and then all the truth tables generated by the gate are based on those logic. Okay, so basically, and also you also can write an expression, right? So we will now try to write expression based on the logic. Now, for an example, if somebody tells you this, that can you write an expression which will be 0 only when all of the variables A, B, C, and D are 1s. Now, first of all, how can I write this expression? This is actually easy, but I have to figure it out. How do I write it? First of all, so if you notice, there are 4 variables here, right? So if you have 4 variables, you should check the table that we have for 4 inputs. Remember, I gave you a table where you have all the gates, like I'm talking about this one. Remember, you already have it, right? So I just brought it here. So let's first look at the truth table. For this case, look at the truth tables with all 4 variables. Now, what the question said is that the output is 0 only when all of the variables are 1s. Now, first of all, I'm actually talking about the very last row, right? Because that is the row where all of the inputs are 1, right? See, A, B, C, and D, all of the inputs are 1. And then question said the output is 0, right? So if you look at the very last row here, the output is 0 for NAND gate, right? Output is 0 for NOR gate. But if you read the question very carefully, question said only, right? I actually highlighted the word only. Now that means that this gate will give you 0 only this time. Which is the gate? Obviously NAND gate, right? Because if you look at the column for the NAND gate, NAND and NOR both gives you 0 when all the inputs are 0, but NOR gives you 0 in many other times, right? But the NAND gate gives you 0 only at this time. So the logic is actually talking about the NAND expression. So that means, to make it simple, I have to write the expression for NAND gate with 4 inputs. What the NAND gate does? The NAND gate actually ends all the gate and then invert it, right? So basically this is the expression. We have 4 inputs, A, B, and C, D, and then we put a parenthesis and put a prime. The reason we put a parenthesis is because the actual expression is A, B, C, D whole bar. We cannot write bar all the time, right? Especially in pause, you cannot write the bar. So instead of writing the bar, we write the primes, which is pretty much the same thing, but we put the parentheses so that everybody understands the prime is actually applied on the whole expression. Okay? But this is similar, just similar to the NAND expression. Whenever we talked about the NAND gate for the first time, we had only two inputs, A and B, right? But now I have four inputs. It's pretty same, because at that time you had A and B inside the parentheses. Now I have A, B, C, and D inside the parentheses because you have four inputs. Okay. So we'll try some logic expression based on the logic given in the question. Most of this question will be answered based on the truth table that you have. All you have to do is you actually have to find out which specific gate and which combination of the input we are addressing in the question. Okay. Now remember, all these Boolean expression, the one that we are writing, belong to an algebra called Boolean algebra. It's just like our traditional algebra. The only difference is this. We have variables in the Boolean algebra, but every single variable can take only two values, 0 and 1. In the traditional algebra, any variable can take any value, right? But in the Boolean algebra, it's actually simplified because we just have the variable, we will have the variable which can take only two values, 0 and 1, right? Now, since this is a new different type of algebra, we want to make sure that what kind of laws this algebra follows. Okay? We'll probably understand a little bit better if I look at some example. Let's say in this algebra, A plus B is also equivalent to B plus A. You might be wondering why it is so important that to understand A plus B equals to B plus C. Trust me, in different types of algebras, this is not valid because there are different types of algebra. I'm saying we're not talking about only the traditional and Boolean algebra. There are plenty of different types of algebra where this expression is not valid. But in the Boolean algebra, this is valid. Remember, this is also valid in traditional algebra, but we want to make sure that this is also valid in Boolean algebra. This is called commutative law. Okay? There is another version of the commutative law which comes from the AND gate. As you can see, this is from OR gate, right? So that means if you write A plus B or if you write B plus A, those are the same thing. Or if you write AB, meaning A times B, or B times A, those are same thing. Okay? We actually write it in the traditional algebra, but sometimes we probably don't realize that these probably are possible because we have some laws and all these laws have some proofs. We're not going over the proofs, but I'm just trying to give you the reference. So these are called commutative law. Now there is something called associative law that actually tells that, for an example, if you look at these three variables here, in the left side, we actually ORed B plus A first, and then we did A later, right? But in the right side, we did the A plus B first, and then C later. But in the Boolean algebra, this is actually the same thing. Same is true for the multiplication. If you do B and C first multiplied, and then multiplied A later, is actually the same thing like A and B multiplied and C later. Okay? This is the associative law. And this is the third and the last one, which is called distributive law. This actually tells that you can take common factor and you can also distribute it. So for an example, if you have something like this, you can distribute A to B and C, right? So I'm sure that if you have seen the traditional algebra, all these three laws are also followed by the traditional algebra. So this is pretty similar. So we can do pretty much the same, but to understand the distributive law better, I also tried to draw two different circuits. Because remember, Boolean algebra is not only the expression, because every expression comes with a circuit, right? So if you take the left side expression, we can draw the circuit we have at the right side, right? And if you take the right side expression, we can draw the circuit at the left side. Now, if you look at these two circuits, both circuits look different, right? Because here we have just one OR gate followed by an AND gate because we are just adding B and C and then we are multiplying with A, right? But here we are multiplying A and B, we are multiplying A and C, and then we are adding both of those, right? The circuit looks different, but still they are equivalent. That actually means that even if the circuit looks different, for every single combination of A, B, and C, the output will be same in both circuits. This is really interesting because everything you are writing as an expression, those also should be verified by the circuit. Okay, so whatever we are claiming, oh, this is true in the expression, but don't forget that that expression has a circuit. Okay, every expression has a circuit. So this is also true in the expression. If you want, you can try it with every single combination of A, B, and C. There are 8 combinations for A, B, and C, right? 2 to the 3, 8 combinations. For every combination, whatever the x you will get at the left side, you'll get the same x at the right side for every combination. That actually means that both of the circuit looks different, but they will give you the same output. That means they're actually the same equivalent circuit. So what we want to know is, given an equivalent expression, can you tell us which law we applied to that expression? For an example, look at the equivalence here. So we actually did an equivalence. Can you tell us from the list that which law we applied to this expression? We have 3 laws, right? Commutative law, associative law, and distributive law. So the right answer is distributive law, right? Because as you can see, we actually distributed D, right? See, we distribute D here, we distributed D here, right? How about this one? This is actually the first one, right? The commutative law. Because we just changed the order, right? Because the commutative law tells you that if you change the order, it doesn't matter. Because if you just write A plus B or B plus C, or if you just write AB or BA, are the same thing. We actually, as you can see, we changed the order because we wrote the SE later. We even changed the ordering in BDE because instead of BDE, we wrote BBE. So all of these belong to the commutative law, right? How about this one? So the ordering is fine here. The problem is we actually changed the association, right? So if you look at this one here, we added this AC and BD first and EF later. But in the second part, we added BD and EF and then added the AC in separate step, right? So that means this is the associative law, okay? So in our next quiz, which is quiz 12, we'll give you all this sort of expression, and then you have to identify which law is applied out of the 3 laws that we have for the Boolean algebra. This is actually the very last one for today in this lecture. There is a very interesting law, and you will see a lot of applications of this theorem in the later part of chapter 4 and chapter 5 also. This is called De Morgan's theorem, okay? Now, again, I tried to give the bar here, but you know the bar is prime, right? We can always write the bar as prime, but I still give you the bar here because sometimes I feel like it's easy to understand with the bar, but you understand also that bar can be replaced by the prime, right? So there are 2 different forms of the De Morgan's theorem. The first form tells that AB whole bar equals to A bar plus B bar. This is how I actually see it, okay? If you try to remember it, this is how I try to remember. So for an example, if you think AB bar, that means this, there is a dot, right? We don't write the dot though, but there is a dot in between A and B, right? Because that is multiplication, right? Now, in the right side, what we did is we actually break the bar, right? But if you break the bar, the dot becomes plus. That is how actually I want to remember it, because, and this is also interesting, if you draw the circuit for both, as you can realize that the left side is just an NAND gate, right? But the right side is 2 inverter followed by OR gate, right? Because A bar means A followed by a bubble, right? Remember, any bubble, if it is not, if that doesn't belong to NAND gate or NOR gate, that is an inverter, right? So this is an inverter here, this is an inverter here, and then after the inversion, you have an OR gate. So both of these gates will actually give you the same output if you check the combination of A, B, and C, and that's what I actually did here. So I actually tried to give you the list of all the input combinations, and as you can see, the output column is pretty same for both. It's exactly same for both circuit. This is the second part of the De Morgan. This is still the same thing. Remember, if you look at the second part, this is still same. Look at this. I have a whole bar here, but if I break the bar, the plus becomes dot, right? So the idea is still same, That means if you have a whole bar, if you break the bar, plus and dot flips. If there is a plus, it flips to dot. If there is a dot, it flips to plus. And again, we try to show you that both of the different gates, they look different, but for every single combination of A and B, there are 4 combinations, right? Because we just have 2 inputs. 2 squared is what? 4, right? So 4 combinations. For every combination, both circuit will give you the same output, at exactly same output at the X column. That actually means that they are equivalent. This is a very famous theorem. This looks very simple, but this has a plenty of interesting applications which will be coming in our future lecture, not right now, because at this point we are just trying to understand the theorem and try to apply it. So to apply it, I try to give you some example here. So for an example, let's say I have an expression here, and if you have to apply the De Morgan theorem, how do you do it? You first break the bar here, right? Because there is a whole bar. Do you see the whole bar? If you break the bar here, the plus becomes dot. That's exactly what happened here. And then there is a C which has a double bar. Now remember, double bar actually means the same thing, right? Why? Because double bar means you're inverting twice. If you invert something twice, that gives you the same thing, right? Because the 0 becomes 1 and then 1 becomes 0 again. So that's why we can eliminate the double bar. So there is a double bar here. We cancel the double bar, which gives you only C, because double bar means the same thing. So I have another expression here, and then I have to apply the De Morgan. So I'll pretty much do the same. There is a whole bar, right? This is a whole bar, right? So what I'm going to do is I'll break the bar here. If I break the bar, the dot becomes plus. And then I have a double bar on top of C, which cancels, right? Anytime if you have double bar, you can safely cancel it, because double bar actually means the same thing, because you're inverting twice. That will give you still the same. That will still give you the same output for that combination. Let's try another one. We'll apply the De Morgan's here again. So we'll first start with this whole bar. So we always start with the whole bar. So there is a whole bar here, right? So if we start with the whole bar, we break the bar, right? We break the bar here at the middle. If we break the bar, there is a plus, right? Which changed to dot. So again, there is a double bar here. There is a double bar here which get cancelled. So it becomes A, B, C, D. So there are dots. This actually means A dot, B dot, C dot, D, right? But we don't write the dots. I still showed you the dot here so that you can see that plus is flipping to dot. Sometimes I write dot just to make sure you can see that there is a dot. Even if I don't write dot, there are dots, right? Because there is a dot here. I don't have to write it, so I did not write it here. But I wanted to show you that this plus is actually flipped to dot because of the De Morgan's theorem. Because anytime you break the bar, the plus and dot flips. That's exactly what it is. So in the very last quiz for this lecture, which is quiz number 13 from chapter 4, we'll be actually practicing some expression for De Morgan's theorem. So what we are going to do is we will apply the De Morgan's theorem on the expressions and simplify it as long as we can after applying the De Morgan's. In some of the expressions, you might have to apply the De Morgan's for multiple times. Meaning, if you apply it once, if you still can apply, you will keep applying. Okay. Okay. Let me stop this presentation here so that you can try those quizzes.